Okay, this lesson we're going to learn what's called related rates. It's, I think, one of my favorite sections of calculus to teach and to do myself, maybe for a couple reasons. One, historically, it's the very reason that calculus was developed in the first place by Isaac Newton and others. And also, it's just very applicable to the real world. Okay, it shows how calculus in particular can be used to solve problems that you wouldn't be able to solve without. So, here's an example. It's called related rate. Suppose you have a balloon. I'm not going to write the whole problem on the board, but you have a balloon and it's being inflated with, say, helium or whatever at a rate of 10 cubic inches per second. Okay? And you want to know how fast is the radius increasing when the radius, now use R for the radius, is 5 inches. Okay? So let's think about it. If you've ever seen balloons get inflated, you know that you put them up to the machine and the helium is coming in at a constant rate. And first they kind of grow fairly fast. They start like this and they grow fast. And then as they get bigger, even though the helium's coming in at the same rate, they're not increasing as fast anymore, right? They kind of go like this and then even less and so on. So the rate at which the radius is increasing depends on what the radius is. It increases faster for small radii, and then as the radius gets bigger, then the rate of change of the radius gets smaller. At least it seems that way. Let's see if we're right. So another reason I like these problems is because there's kind of a very standard way to do them, which works for all of them. So it's kind of cool. Here's the first question. You ask, what rate do you want? And in this case, the rate we want is how fast is the radius increasing? And so the rate we want is the rate at which the radius is increasing. So we don't want R, that's not what we're interested in. We're interested in how fast is it increasing. So think about it, that's the derivative of R. That's the rate at which it's increasing. So what we want is dr dt. Okay, that's what we want. I'll just go like this. And we want it at a particular point. We want it when R is equal to 5. So put that in parentheses. We don't use that until later. So that's what we want. Second question. What rate do you know? And in this case, we know that the balloon is being inflated at 10 cubic inches per second. That means the volume is increasing at 10 cubic inches per second. So the rate we know is dV dt, where V stands for volume. Okay, won't write that down, but R is the radius and V is the volume. And I won't put the units in here as long as we understand them from the problem. Here's the third question, and the third one requires no calculus, but it's usually the hardest part of all of these related rate problems. So here's the question. What is a relationship between basically these two things? I'll just say what you want and what you know, basically between 1 and 2. Okay, so here's what I mean. Here's what you're involving with what you want. Here's what you're involving with what you know. So you need a relationship between these two things. And I guess I didn't say it here, I didn't write it down, but this is a spherical balloon. Since it's a spherical balloon, here's the answer to the question. The volume of a sphere is 4/3 pi R cubed. Okay? And I'm going to rewrite this with an emphasis on the fact that both r and v are functions of time. So I'm going to write v of t is equal to this, and here I'm going to put r of t, because both the radius and the volume change with time. Time is the independent variable. These two things are the dependent variables. Okay, fourth step. Differentiate. That is, find the derivatives with respect to t, with respect to time. Related rates, they're all dealing with rates, so your independent variable is always going to be t. So let's go ahead and do both sides, okay? On the left-hand side, we're going to get simply dv dt. And on the right-hand side, we'll have to use a chain rule. 4/3 pi, that's all a constant. So we can leave that right where it is, and the 3 comes down. We use a chain rule here. The 3 comes down, cancels with this 3. We're going to get 4 pi r. I can write r of t, but now that I've done it, I'm just going to write r squared times the derivative of r of t, which is dr dt. Okay, there's the derivative of both sides. And finally, solve. I'll just say solve. So we want to solve this for the thing we want, dr dt. And so we write dr dt in this case is equal to, it's going to be what? dv dt divided by 4 pi r squared. And now we want this rate when r is equal to 5. So now at this point, I put in r equals 5. And we get what? First of all, dv dt, that's 10. 4 pi. R is 5. 5 squared is 25. 25 times 4 is 100. 10 over 100 is 10. So it's going to be 1 over 10 pi. And now we can put in our units. Our units are inches per second. So it's going to be inches per second. And there's our answer. Pretty cool. Two things to note. One is, as we suspected, as r gets bigger, notice that the rate of change of r is going to get smaller. See that? When r gets bigger, you're dividing by something larger in the denominator, so dr dt is going to not be as large. And the second thing I just want you to note again is that, let's use this as an example. If I were to ask, what's the derivative of f of x is equal to x squared at x equal 3, how would you do it? Hopefully you know. There's 3, what do? You first take the derivative, get 2x, put in 3, and you get 6, okay? You know that. Here's what I'm pointing out, that before you put in the 3, you have to first take the derivative. If I had first put in 3 here and said f of 3 was equal to, what is f of 3? Equal to 9, and then said now take the derivative of 9, of course the derivative of 9 is 0. So that's no good. You have to first take the derivative, and then only after you take the derivative with respect to x, then you put in the value. And that's why, similarly, you don't put this in until after you take the derivative. After you do it, then you put it in, and you get your answer. Okay? So that's why I like to put it in parentheses here, just to warn me of that. Okay, let's do another one. I've got several problems. A couple of these I've made up myself, and they're some of my favorite problems that I've made up. And so we'll probably use 2 lessons for this. Here's another one. You've got a tree where the radius is growing. I'm just going to write right off the bat the rate at which the radius of the tree trunk is growing at a rate of 3 inches per year, and the rate at which the height is changing is 10 inches per year. So this is a tree trunk. And you want to know how fast is volume changing when the radius happens to be 10 and the height happens to be 100. Okay, and again, just for ease of space and so on, I'm abbreviating that, but normally in a problem it would just say something like the radius is changing at a certain rate, and the height is changing at a certain rate, and then you've got to realize that you need to put in dr dt and such. Okay, so let's get rid of all this stuff. We'll keep the same questions there, and see what we get. So what rate do you want? We want the rate at which the volume is changing, so let's write dv dt. dv dt, and we want it when r is equal to 10 and when h is equal to 100. Okay, so there we have two things that are variables. What rate do you know? In this case, it's going to be what rates do you know? Okay, what rates do you know? We know two of them. We know the rate at which the radius is changing is 3, and the rate at which the height is changing is 10. Okay, so there's the rates we know. What's the relationship between what we want and what we know? So here we go again. If you want to, just circle those three things. This is I didn't say it right up front, but this is a cylindrical trunk. Okay, the trunk of a tree, it's in the shape of a cylinder. So, what's the relationship between the volume and these two things? Well, maybe you know that the area of a circle is pi r squared, and so if you have yourself a cylinder, it's just going to be pi r squared, which is the base, times the height, and so here the volume is equal to pi r squared h, like that. Okay? Differentiate. Well, I like this problem because it tests you to see whether you remember that you need, in this case, to use the product rule. Let's do it. So again, if I want to, I can write pi times r of t, quantity squared, times h of t. If it helps you to do that, write them like that, because these are all, and this is v of t. Like so. So, here we go. dv dt is equal to, well, let's see, what's the derivative of this thing? I can leave the pi right out front. I'm just going to do it like that. That's going to be times everything in here. And so the derivative of this, let's see, bring the 2 down, it's going to be 2r to the first power times dr dt. So there's the derivative of the first thing, 2r dr dt, times the second thing, h, plus the first thing just the way it is, r squared, times the derivative of the second thing, dh dt. Okay, let's check it again. Here I have the pi out front, so you bring the 2 down, 2r dr dt times h, plus, what's the product rule say? Now you leave this one alone, r squared times the derivative of h, which is dh dt. And now you can put in these values. So here's number 5, which is solve. Here it's everything is set for us, so we can just say dv dt. And I'll say here when r is equal to 10 and h is equal to 100. So it's going to be pi times 2r. This is, well, r is equal to 10, so it's going to be 2 times 10 times dr dt, which is 3, times h, which is 100, plus r squared. R is 10 again, so 10 squared is going to be 100, times dh dt, and dH dt is, you know what? Just so we don't have so many 10s in here, I think I meant this to be an 8. So let me change that to an 8. Just so that if you want to look at this later on, you'll doggone it, I should have made that. That's an 8 then as well. Okay, so that way you don't have so many 10s. So dH dt is 8. This dH dt is 8. And so now we have this dr dt, h, r squared, dH dt is going to be 8. Just so you can tell which one means what. So very good. And so here we go. What do we get here? This is 100, 1,000, 6,000, and this is 800. So 6,800 pi. There you go, 6,800 pi, and the units would be what? Cubic inches per year, I guess, right? Per year. So so there you go. Okay, so very standard problem. This is the way they work. Okay, let's stop right there, and I'll do another lesson with 2 more.